Okay, good afternoon. Right, so this could be our last two sessions, this afternoon till 6 o'clock. And I may do like an open session next week where I will be on standby, and then you can come just to join me on Teams if you have any questions. Is that okay? I'll see how it goes today, but I think we can finish today the syllabus, unless I go very slow, in which case we may have another session. But regardless, I will be on standby next Tuesday at 2 o'clock. Sorry, 2 o'clock. So if you have any questions, because your exam is 2 weeks away now, isn't it? Is it the 7th or the 9th? Or is it the 9th? Yeah, so it's like 2 weeks from today. It's like 2 weeks from today. So you haven't got like a lot of time really to revise. I'll talk about the exam later on, okay? But that's the plan. So the plan is for me to try and finish today, so that you have got the next. Well, it will be 1 week because the week after is your exam. So it'll be just last week for your revision, isn't it? So next week will be your revision, and then you have the exam the week after. So you haven't got a lot of time. I didn't do the timetable, so that's how it is. And so I hope you have been revising throughout the module, so you haven't left it really late, because you haven't got really a lot of time, to be honest. I don't know how many exams you have. How many? Three. Is soil one of them? Soil is one of them. I hate soil. Oh, it's been recorded. Not my.
Where did you put the stuff on the asymmetrical frame that you were going to put up?
Is it not there?
I couldn't find it.
I think it was originally meant to be last week.
Please drop me an email, just remind me. I've got it in my. I thought I had uploaded it. Sorry, I will do it. Yeah. Okay. So yield line analysis of slabs, optimization. Today we're going to look at optimization. I mean, we did the examples that we did in the past, especially the rectangular slab. The pattern was actually given to you with all the dimensions. Okay. But what happened if you have got a, okay, I'm not going to go over this. Are you okay with the sign convention? Okay, but we'll cover it anyway now with this example, okay? So what we have is we have a slab, and it's a rectangular slab, simply supported on all four sides, okay? The yield line pattern is given to us. However, what's not given is we don't know where the yield line starts. So we have got this distance x here. Whereas if you try to compare this with the example we did last week, I think that was given to us. Yeah, we had 2 meters or something like that, okay? So in this case, the pattern is standard for a rectangular slab, simply supported. That's the pattern. So that's given, okay? What's not given is that we do not know where the yield line will start, where the yield lines will start. So we assume it's starting at some distance x from the corner, and then we use symmetry, obviously. So the slab is 3 meters in this direction, in the y direction, and 4 meters in the horizontal direction. Okay, and we use symmetry, so we have got x, and what's left in between is 4 minus 2x. Okay, so this is the slab. Given also the moment of resistance in the x direction is m, and the moment of resistance of the slab in the y direction is 0.4 m. Again, that's given, okay? So the question is to determine the optimum value for x to give us the optimum solution in terms of moment of resistance for this particular slab. So that's the question, is what is the optimum value of x to give us an optimum solution for MW, okay? So we I go just over this very quickly for those of you who missed it, okay? So what we define here, we define the moments vectors, the moment vectors, okay, in this red, if you want, color. And the way you obtain the moment vector is you use the right-hand screw rule. So basically, for example, if you take this yield line here for region A, if you take this yield line, your moment is coming out of the screen towards you, isn't it? So that's the moment. So if you make the palm of your hand, that's the direction of the moment, and the thumb will give you the direction of the vector. So the vector in this case, the moment vector is in this direction, okay? So I repeat, so you got your moment coming this way, okay? And use the right hand, and that gives you the thumb will give you the direction of the moment, okay? And you do the same for this yield line and this yield line. It's exactly the same. You've got the moment and the vector, and then for this here, you've got the moment and the vector. For the rotation vector, this region A rotates about this axis here, about this side. Okay, that's the axis of rotation. Okay, so when the slab fails, this region A rotates about this axis. Okay, to get the vector rotation, for the vector rotation, you use the left hand. Okay, so you use right hand for the moments, left hand for the rotation. Okay, so what you have again, you've got the rotation is this way. Okay, when the slab fails for this region here, it rotates this way. Okay, towards the screen. Okay, so again, the thumb gives you the direction of the vector, which is in this direction. Is that clear? Yes. Okay. And you repeat the same for B, C, and D. What I said last week is that you don't have to do it for all regions. If you do it for one region and you know some of the rules that I've explained last week, then you don't need really to do it for all of them. For example, A and C are identical. We have symmetry. So you can see that the moments along a yield line are in equilibrium. So therefore, if this is the direction of the moment vector for A, then for region C, it must be in this direction, because they are in equilibrium. Okay, and the same here for this yield line and this yield line. And then what you notice here is that the moment vectors go like in the same direction, follow the same flow. See that? See what I mean? So they go like in this case from right to left. Okay. They go in this way, okay, and therefore you can see that for the same yield line for regions D, C, and B, you've got the flow going opposite direction like this. Okay, so these are just some of the simple rules, and you can see that the vector rotations, these vectors here in blue, they go around in an anti-clockwise direction like a flow again. Can you see that? So you do it for one region A, or you pick any region. And then following the conditions of equilibrium and the fact that the vectors will go, around, following the same flow, then you can deduce the vectors for the other regions. Okay, so you don't have to spend a lot of time trying to work out the vectors for the other regions. Okay, so you do one, and the rest will just follow. Okay. Once we've done this. Once you know the direction of the vectors and the geometry is given, the next thing is to work out now the works. So you do the internal work and the external work, and then you equate the two for equilibrium. So, and the best way to do it is actually to do it in the form of a table, and I'm going to explain this in a minute. Okay. So for the internal work, the general equation is that for the internal work is the moment times the length of the yield line times the rotation. Why do we, the difference between this and the plastic theory, if you remember, we used to have MP times theta, isn't it? So that's what we do for the internal work. It's MP times theta. The reason we multiply by the length, what's the reason? In the plastic theory, we just take MP times theta, isn't it? Why do we have to multiply here by the length? I did explain it last week. What are the units of M, of the moment, in this case?
It's going along that whole section.
Well, exactly, because the moment, you can see the moment here anyway, applies along the entire length. And the units of moment in the yield line theory, the units are kilonewton meter, which is the unit of moment, per meter, per unit length. Okay, so that's why you need to multiply by the length, because the moments are applied along the entire length of the yield line. Okay, so you multiply by the length. So, and this is what I've done here. So if you take region A, for example, let's start with this one here. You've got, in this column, we've got the regions A, B, C, D. So we have 4 regions. And in this row, you put the M, length, and rotation. Okay, so you put mx, lx, theta x, that's for the x direction, and then you have my, ly, theta y for the y direction. So what you do, you project the vectors, you project these vectors onto the x-axis and onto the y-axis, and then you multiply the moment times length times rotation for each direction, and you add them up together. Okay, so starting with A, follow here this carefully. So starting with A, this is the vector, the moment vectors. Okay, these here in red. Okay, so when you take these vectors here and you project on the x-axis, right? Do you agree that these 2 vectors will give you a positive, a negative moment? Agreed on the x? Yeah. So all these vectors here, all 3 for region A, all 3 vectors projected on the x-axis will give you a negative value, and it's m. Because on the x-axis, this is the maximum moment. That's the moment of resistance. That's the maximum moment you can have. Okay. So when you project these vectors here on the x-axis, it's minus m. Clear? Okay. Now projected on the y-axis, when you project onto the y-axis, do you agree that these 2 here will cancel each other on the y-axis? Yes? So what's left? This vector. And this vector on the y-axis is also 0. So you have 0 there. Clear? So these 2 cancel each other, and this one projected on the y-axis gives 0. So therefore, on the y-axis, we have 0 for region A. Correct? Now, let's look at the yield lines. So for this yield line, this is the yield line for region A. Okay, that's the yield line. All right. Now, look at this yield line here and project it onto the x-axis. Do you agree it's 4? Agreed? So that's the yield line for region A. You project on the x-axis, it gives you 4. Agreed? Yeah. So when you project, so you've got 4 there. So so when you project this yield line now onto the y-axis, what do you get? Don't look at the table, just look at the figure. This is the yield line for region A. Project it onto the y-axis. What does it give you? Look, that's the yield line, okay? Project it onto the y-axis, it gives you this length, which is 1.5. You agree? Yeah? Okay, you're projecting the lines, okay? So when you project onto the y-axis, it's 1.5 meters, okay? Now, the thetas, the angles are the ones that where you need to, to think a little bit, okay? So look at region A again. We are still in region A. Look at region A. Region A rotates about this axis at failure, yeah? So think now in 3D, all right? So the rotation takes place out of plane, away from you towards the screen. Do you agree? So what is the angle of rotation? Remember that the maximum deflection, we always take a unit displacement. Okay, with the yield line, we always take unit displacement, because if you take delta, it will cancel, as we have shown last week. So there is no need to say delta. Okay, so we say that the displacement that we have, a unit displacement, the maximum unit displacement is 1. Okay, so what is the angle of rotation for this region about this axis? Well, I've done it here. That's the that's a you know, looking across here. This is what you get. Okay, you've got a displacement there of 1. Okay, and you've got this length or this length. It doesn't matter because we're talking about very small displacements. Okay, so this is 1.5, and this is 1. So what's the angle? This is 1.5. Okay, and out of plane you have 1. So what's the angle? What is sine theta? Sine theta is opposite over hypotenuse, isn't it? So 1 over 1.5, okay? But remember that the angles are very small, yeah? This is one of the assumptions of the yield line. Just like with the plastic theory, we said that displacements and rotations are very, very small. So if the angle is very small, sine theta is roughly equal to theta in radians, yeah? So you have theta equals 1 over 1.5. Okay, why is it negative? Why is it a minus? Because the vector is negative. It's opposite the direction, isn't it? So it's minus. Okay, so it's 1 over 1.5 and it's minus. So that's the rotation about the x-axis. In other words, that's projecting the vector here about the x-axis. On the y-axis, you can see that this vector here projected on the y-axis gives 0. That's it. So these are all the terms for region A, and all you do now is multiply mx lx theta x plus my times ly times theta y, add them up together, and I think you should get 4m over 1.5, okay? Because you've got m minus by minus is a plus, so you have 4m over 1.5. And then you repeat the same. We know that A and C are identical. Okay, you don't have to do that. You can do it if you want. You will get exactly the same value. So because A and C are identical. So you have 4m over 1.5. Let me explain it now for region B, okay, which is identical to region D, okay? So follow this. Let's look at B. Now B, we have a triangular shape. Okay, we have triangular shape, and these are the vectors for the moments, and this is the rotation vector. So for B, starting with mx. So these are the two vectors for the moments. When you project these two vectors, do you agree that you get 0 onto the x-axis? Agreed? They cancel each other. Okay, so we have 0 there. When you project these two vectors onto the y-axis, you can see that they are both positive, and also the maximum 0.4m. Agreed? Okay, so this is projecting these two vectors onto the x and y axis. For the length, this yield line here, this is the yield line for region B. What is the projection of this yield line onto the x-axis? Do you agree it's x? Projecting the yield line here onto the x-axis. You agree? Onto the y-axis, if you take this yield line, project it onto the x, onto the y-axis, it gives you 3. Yes?
Why is the maximum 0.4 meters?
Given, that's given. These two are given. Yeah, they are given. The moments there, which is not given to you, these moments here depends on the steel reinforcement of the slab. So depending what reinforcement you've got in the x direction and the y direction, you use Eurocode. I think I did explain it last week. So if you use EC2, if you know all the dimensions of the slab, the thickness, and you know the reinforcing bars and the diameters and everything, you should be able to work out the moments of resistance using Eurocode 2. But we are not doing design, so I will always give you these values for the particular problem. Okay, but you can actually get them if you know everything about the slab. All right, from design. Okay, do you agree with these projections now for B, please? Clear? Now, how about the rotation? Now, this region B rotates about this side here, this axis. Yes? right? Okay, and the moment of rotation, the rotation of this region B, I mean, this is 1 here, we have 1 as the maximum displacement, so we have 1 here, and this length is x. Do you agree that the rotation, again, which is out of plane, do you agree it's 1, do you agree it's 1 over x? And again, I've done here a drawing to help you. You see here, I've taken this is x, okay? And then out of plane, we have 1, and the angle is theta, okay? So we have x, and 1 here. So you have sine theta is 1 over x. I mean, remember, again, we are talking about very small displacements and rotations, so this length is the same. So you have x and x, okay? So therefore, you have sine theta is 1 over x, which is what we have here, and it's positive because it's in the positive direction. So we have 1 over x. And this vector projected onto the x-axis will give you 0. Is that clear? Yes or no? Please? Because you're getting just an example like this, similar. Is that clear? If there are any questions, please do ask. Is it clear? Yeah, okay. So when you multiply the ML thetas for x and y directions, it gives you 1.2 m over x, again, identical to d. And then what you do then, add them up all together, which gives you 2 times this value plus 2 times this value, which gives 2m. I've taken 2m here outside the bracket times 2.67 plus 1.2 over x. And that's the internal work only. Okay. As I said earlier, you can save a lot of time. I've gone through it in great details, but to be honest, you can do it in 5-10 minutes using the fact that you have got symmetry in both directions. So you save yourself a lot of problems, a lot of time. Is that okay? Any questions on this slide? Okay. So now what's next? Next, we do the external work for the slab. Again, we are going to use symmetry, and we do the internal work for A or C, and then we do the internal work, the external work for A or C, and then we do the external work for A or B, and then, B and or B, and then we multiply by 2, okay? The external work, again, the definition, it's the UDL times the area on which the UDL is applied, which will be the region, times the displacement. Again, to make the analogy with the plastic theory of structures, in the plastic theory, we used to do what? If we have a UDL, what do you do with the plastic theory? If you have a UDL on a beam, in the plastic theory, what do we used to do? Do you remember? If you have a UDL on a beam? The UDL, the load times average displacement, isn't it? It's exactly the same. The only difference is that you multiply by the area. That's the only difference. Because for a beam, you've got a length. For a slab, you've got an area. Because the UDL is on an area, okay? So you multiply the area here, the load by the area, and then you multiply by the displacement. So it's exactly the same analogy if you want. The only thing is because of we are working in 2-dimensional. So starting with region A or C, this is what we have, okay? We've got 4 minus 2x, x in this direction, in the x direction, and in the y direction, we've got 1.5, and this is the region C. Region C, you can divide it into 3. You've got 2 triangles, identical, and a rectangular shape in the middle. So therefore, we are going to use this. So we have UDL. If I start with the C, so what do we have? We have, for the triangle, can you see that? What's the area? Okay, let's do the rectangle, sorry. Okay, what's the area for the rectangle? 1.5 times 4 minus 2x, okay? Times displacement. Remember, the maximum displacement is 1 here, isn't it? So at the centroid, it's 1 over 2, okay? plus the area of the triangle. What is the area of the triangle? X times 1.5 half. Agreed? And then we multiply by 2 because we have 2 triangles, and the displacement will be a third because you've got 1 here, and the centroid is at 1/3, so that gives you 1/3. Okay, because the displacement is 1, maximum is 1 there, and then we take the at the centroid, so you have 1/3. Okay, and that's the external work for C. And then what you do, you expand and then you state the fact that the external work for C and A is the same because they are identical. Okay. For region B or D, what do we have? I mean, if I take you back, so we've got these 2 here, which we have done. Now we're going to do D or B. Okay. So this is the region D. We have a triangular shape, 3 in this direction and X in this direction. Okay. So we use the definition again. So it will be W. What's the area? What is the area of the triangle? What's the area of the triangle? You have a triangle here. What's the area? Come on. Is it all gone? What's the area? Yeah, 3 times x over 2. Yeah, I want to hear the 3 times x over 2. Okay, no, that's fine. So it's half the base times the height. Yeah, always. Okay, so we've got, and then you multiply by the displacement again at the centroid, which is 1/3. Okay, simple. Yes.
I have a question. Centroid of a triangle will always be a third.
Yeah.
And then for a rectangle
Yeah.
as
Yeah.
well.
Yes. Yeah. Yeah. It's 2/3 from the base, 1/3 there. You've got 1 here, so it will be 1/3 at that point. Yeah. Okay, so now, and then we say that the B and D are identical, so we've got the 2 are equals. So now what I'm going to do, I'm taking this one here, plus this expression, and times by 2 to give me the total external work, okay, which I've done here. So the external work will be twice the external work of C and twice of B, and then what you need to do, just expand the brackets here, and you will see that there will be some simplifications, and you get 6W minus WX. I've taken the W here, outside the bracket, 6 minus 6. And that's the total external work for this slab. So now we know the internal work, and we know the external work, and we're going to put the 2 together for equilibrium. External work equals internal work. Are there any questions? Anything at all? Clear? Okay. So we have total external work equals internal work, right? So equilibrium. So we put the 2 together, as I said. So you've got W6 minus X equals to the internal work, sorry, which gives me this. Okay. Now that means that W is 2m times 2.67 plus 1.2 over this, or if you want, you can get m equals W times that. All right. So this is equating the external work and the internal work, and then you can deduce either the load or the moment. All right, depending on the question. So we've got what we have here. We've got the moment of resistance. The load usually is given. Okay, usually you know the load you're applying onto your slab. So therefore, what we see here, we see that the moment m is actually a function of the distance x only. Right? And remember, the distance x is unknown, so we don't know what the question was to see to find the value of x, which gives us the optimum solution. So in order to do that, we need to optimize this expression here about m. And when we say optimize, from a mathematical point of view, that means dm over dx, isn't it? That means you differentiate this function about x and put it equal to 0. Okay, which is what we have done, which is what we have here. So to find the optimum value, you differentiate this expression here about x equal to 0. If you do that, you get this expression, and it gives you this solution. Okay. And what I've done here on the next slide here is for those of you who are not very sure how to get this expression, I have done it here. Okay. So let me go through it. So we have m equals to this. Okay. I've taken the 2 here outside the bracket. So we have w over 2 times 6x minus x squares over this. Okay. Now for optimum value, what you do, you are going to differentiate this here about x equal to 0. Okay. So what I've done then, I've put u equals to 6x minus x squared, and I put v, the denominator here, v 267x plus 1.2. So we have m is equals to w over 2 times u over v. In order to optimize, w over 2 is positive, so you can ignore it. You can forget about it, okay? Because we are going to optimize and equate to 0. When you put it equal to 0, w over 2 cannot be 0, all right? So the only thing that can be 0 is the when you differentiate this ratio here. Are you familiar with this? When you have u over v and you differentiate it, u dash v minus v dash u over v square. Familiar with this? Or not? If you have a ratio. Yeah, if you have an expression over an expression equal and you differentiate it, so it's the derivative of u times v minus the derivative of v times u over v square equals 0. Okay, so when you, because the denominator cannot be 0, you can't have the denominator 0, so the only thing left is the numerator here. So what you need u dash v minus v dash u equals 0. What is u dash? What's the derivative of u?
6 minus 2.
Yeah, 6 minus 2x, isn't it? What's the derivative of v? Derivative of v will be 2.67. Agreed? Yeah. So when we do u dash v times v minus v dash u, so we substitute in the expressions here, and when you develop the equation, when you expand, you get minus 2.67 x squared minus 2.4x plus 7.2. What I've done, I've multiplied everywhere by 2 just to make it look like this here, and then transpose or transfer everything to the other side, which gives 5.34 x squared plus 4.8 x minus 14.4. And this is a quadratic equation. Are you all comfortable solving quadratic equations? GCSE, maths? Just because I had this here in the handout I have uploaded on Aula, that's the only reason. You don't have to. It doesn't make any difference to the solution. It will be exactly the same. Yeah, because it's equal to 0. So it doesn't matter. You multiply 2 or 3 or 4, it doesn't affect the solution. So what we have a, so this is the form ax squared plus bx plus c, where a is 534, b is 4.8, c is minus 14.4. So you have delta. I think you're all familiar with this. So you work out delta b squared minus 4ac, and you have 2 possible solutions, minus b plus square root of delta over 2a, or minus b minus square root of delta over 2a. If you calculate delta from here, you find 330.62, and the first solution will give you minus 251, and the second solution with the minus here, with the plus, sorry, will give you 1.25. Obviously, this solution is rejected. We can't have a distance which is negative for the slab. So, and the only acceptable solution is 1.25 meters. So the optimum value for x is 1.25. okay? And if you substitute this value back into the equation of m here, you get this solution. M is 0.66 W. So now we have got a relationship between the moment of resistance and the uniformly distributed load on the slab. Depending on the problem, if you know the load, you can deduce the moment of resistance, or as is usually the case in practice, you would know M from design. So you use a Euro code, it will give you the moment M, and then you can then get the critical load of the the critical load W that will fail, make the slab fail. And that concludes this problem here. And you can see that we've started with the slab where the X values were unknown, so we had no idea where the yield line starts, and then we obtained the solution for that. In this case, 1.25 meters. One point here, and I've seen this in the exam all the time, unfortunately, people get an answer and they don't even reflect on it, okay? So if I get X here equals 3 meters, for example, I made a mistake, and you get 3 meters here, would you accept it? You wouldn't, because the length is 4 meters. So you have X and X, right? So if you have 3 and 3, 6 meters, that's already bigger than the length of the slab. Do you get what I mean? So please don't accept any values that you get here. Always try to think whether whether the value you're getting is actually sensible or not, as engineers. Okay, so you go back to your problem and then see whether it happens all the time. We all make mistakes, and you get 2.5, for example, which gives you 2.55 bigger than 4. So reject it. At least if you make a mistake in an exam and you tell me no, that's not acceptable, because I'll give you a full mark for it. But if you give me a silly answer and you don't even reflect on it, that drives me mad. I tell you this. I don't like, because as engineers, you need to really look at, especially in mechanics, there's always a way of reflecting on your answers and see whether they make sense or not, okay? So please do that, okay? Any questions? Anything at all, okay? Is it what time is it? Because we have to change room, isn't it? In a bit, okay. Okay, no questions? Okay. I will finish with this, and then we move to the next. Okay, this is the equation. Okay, that we had. There is a way. If you hate differentiating and solving, getting delta and solving a quadratic equation, and maybe because you don't manipulating too many questions, there is a way, and I give you a choice in the exam. If you get a solution, whatever solution, if you get a problem similar, if you want to use a graphical solution, go for it, okay? All you need a graph paper, obviously, so you do it properly. So what you need, what I've done here, I've taken the M over W ratio, which is 6x minus x squared over this, and then I've plotted the graph. So what I've done, I've taken M over W here and X. I did a table, which is not shown here, sorry. So what you need, you do a table of M over W, give some values for X. I've taken values of X of 1, 2, 3, 4, 5, 6. Okay? Right? I know that X, because the width of the slab is 4 meters, isn't it? So your X cannot be bigger than 2 anyway. I mean, although the graph here, you can see, I've done it up to 6, but really, my graph really should stop here for practical reasons. You see what I mean? Does it make sense what I'm saying? Yeah, my graph really should stop here, because I can't have X bigger than 2, because you've got 4 meters. Clear? So that the absolute maximum you can have for X is 2. So anyway, I've done it for all these points just to show you how to show you the shape of the diagram. And you can see that by plotting these values here, I've got an optimum value for this ratio here of 0.7. So If you do graphical solution, you can get a, 1 decimal place precision, which is not bad, 0.66. It's very close to 0.7. Okay, so if you do it on a nicely on a graph paper, this is what you get. You get 0.7, which is perfectly acceptable to 1 decimal place precision. Is that okay? So yeah, and that's a lot quicker, isn't it? Because all you need to do is give some values for x here, and then plot a graph, and then get your value. So it's a lot quicker. It's probably a quarter of what you would spend, solving a differentiating and solving a quadratic equation. So the choice is entirely up to you how you want to do it. Yes.
We just plug it into a graph.
You mean if you have a calculator that does a graph for you?
For Excel.
That's cheating. No, it's not acceptable. I tell you why it's not acceptable, because in the exam paper it tells you for full marks you need to show your working. Yeah.
Use Excel instead of TCA.
You may get a mark for it, not 0, but you want to get a full mark. Okay. To get a full mark, I don't mind if you. That's a lot easier if you do it graphically this way, and you have a table with x and m over w values like this, and you plot it. That's okay. It doesn't take you 10 minutes to do. Okay. Is that okay?
What
Yeah.
if you did it using Excel, because it's time controlled assessment? So it'd be quicker than writing it on paper.
Yeah, if you do an Excel and it's your own work, you've done an Excel with the table of the values, that's fine. As long as you go you show me the working. Because with the internet nowadays, you can do all sorts of things. Even if you get a complex frame, you plug it into some of the free software on the internet, it gives you the solution easily. Okay, so but for the examination purposes, you need to show your working if you want to get full marks. That's all I'm saying. Okay, right? I mean, if you have got time, I doubt you will have all that time in your hands. If you have time to check your working with solution from software, go for it. I don't mind, because I'm not there to see you. But I think for the exam purpose, you need to show your working. That's all I'm saying. Okay. Remember, the exam is 4 hours. I think it's 6 o'clock to 10. But you need to finish it within 4 hours. And the reason we give you, I tell you, the exam really is 2 hours. That's how much it used to be pre-COVID. But you get 4 hours to give you the time to do that kind of stuff where you take photos and then scan them and put them into your exam and so on. Okay, so it's just to make up for that. Any questions? No. I don't think I can. It's 1:45, so we'll move room. You'll have 5 minutes break just to move over there. Okay, thank you. So I'm going to stop the recording, okay?